So in all of these analyses, we decompose the flow field into two parts. One is Q0, we call the base flow, and also an infinitesimal epsilon times the perturbation in the flow field. We started with the axisymmetric base flow, Q0. And because Q0 is axisymmetric, you can look at Q primes that are of these kind of individual modes that are a perturbation that is only a function of R and Z times a time component that has a growth term and the frequency term, plus also a mode in the Z direction as azimuthal direction. And we can try different amps to see which mode grows the fastest. And there are two interesting modes we got. One mode is omega equal to 0, that means a steady state mode, and m is equal to 1. And the other mode we get is omega not equal to 0, an unsteady mode, with m also equal to 1. So if we look at the sigma, which is the rate of growth of that perturbation, we find that when the steady mode, omega equal to 0 mode, becomes positive, it coincides with when the DNS stops being steady, being axisymmetric. So that is pretty good. But when we look at the unsteady mode, it doesn't correspond to when the unsteady mode becomes unstable, it doesn't correspond to when the flow field becomes unstable. The reason for that is because we have been using an axisymmetric base flow. And after passing Reynolds number 400 and something, the flow stops being axisymmetric. Now that requires us to perform stability analysis with a completely 3D, non-axisymmetric base flow. So if we do that, then the perturbation Q prime cannot be assumed to have a single azimuthal mode. So we have to have the Q3D to be also an arbitrary function of theta, and we solve a lot bigger eigenvalue problem for computing that Q prime. With that, we get an unsteady mode that looks like that. It's also non-axisymmetric. And when that particular unsteady mode, which is shown in black here, becomes positive, that coincides exactly when the DNS becomes unsteady. And also the frequency omega of that unsteady mode, shown also in black, agrees with the Stokes number computed in the DNS, while the red line computed from the axisymmetric base flow does not coincide with the frequency. Okay, and the last thing, when the flow becomes aperiodic, our base flow Q0 now can be seen as the whole unsteady flow field. So here we perform Lyapunov stability analysis. And now here, the Q prime can also no longer be assumed to be not a function of time. So we have the Q prime having a growth term that is e to the lambda t. That corresponds to the divergence or convergence of that mode. So lambda here is the Lyapunov exponent. And the Q hat, we call it 4D. It's actually a function of the Q0 at that particular time. So implicitly, it's a function of spatial and temporal coordinates. So that is the covariant Lyapunov vectors we can compute. And this is an example of the kind of Lyapunov covariant vector we computed at Reynolds number 900 when the flow starts to become chaotic. And this is the leading Lyapunov exponent with a lambda positive. That means it's a growing mode.